analysis crashes. And I am going to stop this because my bandwidth is bad. Hello. All right. And I'm going to share screen. All right. And one other thing, and that is that I think I should plug in. That's why. All right, so up to this point in PCAM, we have been talking about the world at the subatomic level. We've been doing quantum mechanics. We've been talking about where the electrons go. We have been talking about solving the Schrödinger equation. But as you may have realized, most of us do not live in the quantum mechanics world. Most of us live in the macroscopic world, where things are larger than that. Sorry. Plugged in. Now what's missing? I am not seeing the right thing. You are plugged in the way you're seeing this. And the Zoom controls are blocking exactly what I need to touch. Right. This is what you need to see. Out of the way. Right. I think it's locked. Stop. This one. Come over. How can I move this thing? Okay, there we go. All right, so hopefully now you can do this. All right, so what we're going to talk about is the ideal gases. Now, you've probably heard about EV equals nRT already. So it's not news to you. It's a very simple equation to use. And that's great. There's a lot more to PV equals nRT than you might think. And I'm making you of that today. So the reason why we spend so much time studying this and why we have a whole lecture on it is because, in fact, in the quantum, once we get into the macroscopic world, which is how we call the rest of PChem, which does not deal with subatomic parts, we will be needing to work with things that are bigger than, subatomic particles. And as it turns out, just like we had issues with modeling in the subatomic level and had to make some assumptions, so too this will be the case in the macroscopic world. And guess what? Many of the things that we study in the macroscopic world are modeled as ideal gases. And this might be a bit of a surprise to you, but that is how it is. All right, so the ideal gas equation. The ideal gas equation is PV equals nRT in its simplest form. So let's write that down. PV is nRT. All right, this is pressure. Volume, N is the number of particles, R is the ideal gas constant, and T is your temperature. And the assumption is that all gases
I was like, oh, that's actually really cool.
behave ideally when they're sufficiently dilute. So what does that mean? Well, this is the ideal conditions. And as you might guess where we're going with this, it is not always ideal conditions. But let's see what this would be. So think about what would make this be the most true, right? So when this would be the case would be when you have a high temperature. That would make the particles move around more, and so they would be next to each other the least, right? When gases get hot, they expand, right? The other opportunity that will make this be true is that the pressure is low. Also, that means they're not being squished next to each other, so they're not interacting very much. We also have some other assumptions that they are point masses, which means they have no size or shape. right? They're a point mass, which of course is obviously just a construct. And also the particles are non-interacting. So these things will be true when the temperature is high or the pressure is low, and these are the ideal conditions. So guess when non-ideality happens? Non-ideality is the opposite of the ideal conditions, right? So this is when ideal breaks. And that's when this will happen. All right. So let us now consider two versions of this equation. So we've already had PV equals nRT, but I also want to put another equation right next to it. EV bar equals RT. The only difference is this V bar, and we have regular V over here and then the N. So what this is V bar is defined to be the molar volume. This is the volume per mole. At first glance, you might say, well, you know, who cares about that? Well, the reason why it's important is because of extensive versus intensive properties.
You know, you can use your iPad but now.
And this will become important in thermodynamics. So extensive means that it's directly proportional to the size of the system, like the volume. But intensive means it doesn't depend on the size of the system. It's something that's more or less always true, like pressure, temperature, and density. So what we do is by converting from V to V bar is we are able to convert from something that does depend on the size to something that does not. So let's capture this. We'll have extensive. An extensive property is directly proportional. Proportional to size of the system, whereas intensive does not. On size of the system. So this would be P, temperature, density. Those are all things. So what this means then is that by converting from V to V bar, we've effectively changed from extensive to intensive. Sneaky, huh? All right, so that is the ideal gas and the molar version of it. The next thing I want to talk about is calculating the pressure. I mean, you just like turn on the news, right? Look it up in the app. How do you get the pressure of something? We get the atmospheric pressure from the weather. Now, but you may have heard of like mmHgs for units of pressure. So let's understand how we can actually calculate this. Did you ever wonder? So we have pressure equals force per unit area, right? Know this from physics, right? So force per unit area. How can we use the height of a column of mercury to measure pressure?
Yeah.
So a lot of these thermometers aren't used anymore because, of course, consuming mercury is a bad idea. But in fact, this is actually how the very early thermometers works. So the situation is actually a pretty simple one. It works like this. So you have a tube. This is like a glass test tube. Sure you can tell from my sketch, right? And it's gonna have a vacuum up at the top. And down here, it's gonna be filled with some liquid mercury. That's the mercury, and it is sealed by being immersed in a dish like this. So usually there's water here or some other liquid, doesn't actually matter. Right? But the point is that the dish is full so that this creates a vacuum up here. All right, so now let's begin with the formula. Right. Pressure equals force per unit area. We already said that. Now, the next thing I'm gonna do is I'm gonna sub in force equals mg. Why is that? So if you remember from physics, this is your mass, and g is your gravitational acceleration constant. So we're assuming, we're on Earth and that there is gravity present. So then we can write P equals, now the force is replaced by mg over the area. So I just substituted it. Now I'm going to make another given, which you may not believe at first, but I will show you how it works. Given rho H A equals M. Bam. What the heck is this? All right, so let's just make a little aside over here and make some notes about what this is. So this rho, this is density. H is height. A is area. And is volume. Now, let us also do a little calculation over here about this, what I have just done. All right, so look at this equation here. Rho, oops, no, that's not rho. Just kidding. Rho HA equals M. I'm gonna do some unit analysis here. All right, rho is gonna be the density. That's mass per unit volume. What is the unit? Then we have height. And we have area, which is length times width. And so now we can do some canceling here. We'll get M over V times V, which is equal to the mass. And that is why this is a substitution we could use. So now I'm gonna come back to where I was before. So we had M right here. And now I can plug this equivalency in. So I can write P equals rho H A times G over A, and now the A's canceled. And now I get, okay, so this was sub in, and this is simplified. So I get the pressure equals rho Hg. All right, so now the pressure can be calculated knowing just the density and the height and of course the gravity. So let me show you how you can do it. Calculate the pressure exerted by 76.000 centimeter column. That's centimeters. of mercury. The density of mercury, this is rho of Hg, equals, and of course, this is just a table lookup value would need to be given, grams per centimeter cubed. So how do we solve it? Let's write the formula. Right, so P equals F over A equals rho Hg, which we just did. Now we sub in the data. So we do equals 13.59 grams per cm cubed times the 76. That's a lot of figs here, but that's apparently they can measure it. That's that good. And then 980.67. This is the gravitational constant. You do not remember from physics. And we would substitute and use the calculator to get the answer. So this is 1.013 times 10 to the 6th grams per centimeter second squared. And this is how we can use that in order to calculate. All right. Moving on. Let's talk about temperature. It's another thing in the equation, PV equals nRT. Let's talk about temperature next. What is it? I mean, it's when you walk outside and ask how cold it is. What is T? Did you ever wonder why we need the Kelvin scale since we already have Celsius? We have Fahrenheit too. I mean, maybe you understand, oh, Celsius helps us understand about the temperature so that it ranges from 0 to 100 to scale with the scale of water. And that makes sense why we'd have Celsius scale, and a lot of our world is dominated by water. But there's also some other important things that that these two scales do not deal with. And there is such thing as the minimum temperature, the absolute zero. So establishing absolute zero. The reason why this is important is because that says that then when we compare two things, we're comparing them from a common reference point. You've probably heard of this before. It's the temperature at which all thermal motion ceases. Actually, we'll have more to say about that later. And volume is zero. This is obviously a theoretical construct. All right. So if there are point masses and there's no motion, then the volume is zero. That's the idea here. Yeah, so it's the theoretical construct. Just in case. And absolute zero is set to 0 Kelvin.
Well,
All right, so we'll have some things we need to understand how this is happening. All right, so we have a derivation to do. So the ideal gas law says, where we start. So I'm going to use the molar version, which we introduced before, PV equals RT. All right, now we're going to solve for T. I'm just going to rearrange, and I would get the T equals PV bar over R. Nothing too surprising here. Now, the gases behave ideally when the pressure is approximately equal to 0, right?
Oh, okay, they all have the good.
Pressure is approximately equal to 0. So for an ideal gas, what we're going to do is we take the limit as the pressure goes to 0. So let's remember our calculus a little bit. So we're gonna do limit as p goes to 0 of this thing. So t, this is what we're doing. T equals then p goes to 0, PV bar over R. Now, there's also a few other things we can say here, and that is it possible for the pressure to be a negative number? It is not possible for pressure to be negative, so I will put a little plus sign up here. How about volume? It is not possible to have a volume less than 0, so I will put a little plus here. What about R? Well, that's a constant. So that's a positive number. So this means we have all three positive numbers. So what does this say? This says that this whole side over here could not be negative. So what that means is the lowest possible value for T is going to be 0 Kelvin.
I had one day we just woke up and decided not to.
So the interesting thing is that, I mean, we said, oh, you know, it makes sense that that it is going to be 0, right? The volume will be 0 under ideal conditions. But what we've just done is we've just shown that it could not be negative. There's no way that could happen. And so this is very interesting because this then is saying this from a much stronger standpoint other than just, you know, but 0 seems like a good number. All right, next thing we need to do is establish the unit size of 1 Kelvin. So we may be aware that the unit size of 1 Kelvin is the same unit size as 1 degree Celsius. How to establish the unit size of 1 Kelvin. All right, so it's relative to the triple point, and that's the temperature at which there exists solid, liquid, and gas under the standard pressure. So the Kelvin is defined to be, remember, triple equals means defined to be 1 over 273.16. That number should ring a bell. That is the triple point of water. All right, so then the next thing we can show is more evidence that the absolute 0 value is in fact 0. So I'm going to copy a figure for you. Let's see if I can enjoy my beautiful artistry here. Okay, so we have the x-axis over here and the y-axis over here. It's going to mean something. And we're going to have, let's see, hopefully I did this. Ah, good, yes. So there should be 4 marks. This is going to be, this is 2,000, this is 1,000. This is going to be V bar in units of liters per mole. All right, and that's good because we said V bar should be molar, which it is. And now we're going to have some temperature on the x-axis. So let's take this off. Let's say this is 100. This is going to be 200. It's going to be 300, right? And so forth. All right, like that. Now, what we're going to do is we're going to see how to do the linearization of an equation, and then we're going to plot it. So you may have done this in algebra class a long time ago, but it's very useful to know how to do this because if you ever want to derive something yourself, maybe from your experiments in the lab for writing your papers, this is very useful. And in fact, before we had like Excel and all the other tools we have now, where you just plug in and you like click a button and say, you know, make the line, or being able to plot in other things besides lines. Like suppose you have a curve, right, for your output. What people always used to do is they used to linearize it. If you've done gel electrophoresis, and which migrates in the gel exponentially. What do? We linearize it. You make the semi-log plot, which is basically a linearization of an equation. So it's a very useful thing to know how to do. Because what you can do is you can basically take any equation of interest to you, and then you can attempt to put it in a line, and then what you do is you take that and you look to see how similar the thing you're actually looking at with data actually matches the line. And this is why it's important. All right, so what I've done is I've written PV bar equals R3, and I just solved for V while I was chatting here. So now what I'm gonna do is, well, would you be okay if I said that the volume is a function of temperature? I mean, that doesn't change the equation really, but it does emphasize a meaning. So what this says is V bar of T equals, so now if that is an equation, now T becomes the variable. So that means R over P times T. Sorry, this is kind of sloppy. Let's clean this up. Make it nice and neat. Here, I'll just write it again. That means we have R over P times T plus 0. Now, do you remember y equals mx plus b? This is y of x, y of t, if you will, equals, well, here, let me write it in the generic form for you. Y of x equals mx plus b. What do we have here? Here's a function. Here's a slope. There's the variable. And then we have the y-intercept, which we didn't have one, so I put plus 0 on there. Y equals mx plus b. And now we can plot it. So this may not sound like rocket science. You might be wondering, well, why is Professor Thayer doing this? And the reason is because we can make graphs of this quite easily. Okay, so what I'm going to do is now I'm going to plot it at different pressures. So when I do this, we cannot always measure the entire thing. So I'm going to put dotted lines down here because some lines we cannot actually readily measure, but it will come out something like this. And this is taken from your supplementary readings if you want to see the more official graph. But this is a sketch. This is 0.010 ATM, 0.020 ATM, 0.030 ATM. But you see, the interesting thing is they're extrapolating the point. That's the 0. So we can interpret the graph and we make some observations. Let me actually write these down for you. So as the pressure increases, the slope decreases. See, we can actually do this. We can look at that. As the pressure increases, the slope decreases. All lines extrapolate to 0 Kelvin. And finally, at 0 Kelvin, all the motion ceases, and we have no volume for the point masses.
For example, you could keep
0 volume. And this makes sense because we have our V bar, and that would also be true of our molar volume as well. So this graph is how we can figure this out and how we can calibrate that situation. So let's derive the volume of an ideal gas. Now you probably actually memorized this number in Gen Chem, but did you ever wonder where it comes from? Let's do the derivation. All right, deriving volume. And who cares about the volume of an ideal gas? It's not real anyways. Well, the reason is because you may be working with some real gases that you need to find out the volume of, because you may to deliver a certain amount. Temperature in the limit of P going to 0. Now what we're going to do is we're going to look at V bar is the limit of pressure. It goes to 0 at 273.15 Kelvin. This will tell us the volume of a gas, temperature, and the limiting ideal case of the pressure. So what we're going to do is, again, we're going to start with given info. Our favorite, PV equals nRT, but we'll use the molar version. All right, now let's see what we can do. Next, we're going to sub in the temp. So I'm going to put in 273.15. That's our triple point. R times H. All right, now watch what will happen. And we can make a plot. P versus PV bar versus P at varying pressures. At the constant temperature of 273.15 kelvins. And we see that as P goes to 0, the V bar goes to a familiar number. So as the conditions get increasingly ideal, right? Because when the pressure is equal to 0, that is the ideal condition. Okay, 22.414. Have you seen this number? Meter atmosphere. Have you seen this number before? Do you remember this one? This is the volume of an ideal gas. But why? You probably use this number in your Gen Chem calculations. I used to teach Gen Chem. All right. So what we're going to do is plot PV bar over pressure. Like so. So the numbers we're going to have here, let's try to make this to scale. Let's see, I have 4 different values. 1, 2, 3, 4. So this is going to be, let's see, 22.3, 22.35. It's a pretty fine scale. 2, and so on. All right, and so we are actually going to need another tick mark up there because the key value is going to be teeny bit bigger than that. It's right about there. So when we make these plots, we're gonna get something like this. Now all of them go like this. And again, if you want to take a look at the more professional graph, don't like my sketches, you're welcome to have a look at the graph in the supplementary readings. Okay, so CO2 comes out down here. This is nitrogen gas. This is ideal gas. And up here we have these non-interacting particles. Is essentially the ideal. Oh, wait, no, that's wrong. Well, yes, these are the non-interacting particles. This gas right here this is the line for H2, right? So it's like this. So these are behaving more ideal, and these are the interacting. And this is less ideal. Now, why do you suppose that might be true? Well, think about this. About the dipole moments. N2 is going to be, well, it's 2 centers that are the same, right? They're pulling the same, but CO2 is going to have a carbon versus oxygen. Oxygen is much more electronegative, so you're going to get partial charges on these, partial atomic charges, so they're going to interact. And that's why these are the least ideal of the ones that are plotted here. So what this shows though is that they all converge up to 22.414, our value from Gen Chem. So in Gen Chem, we told you what it was, and now you have some idea as to why it's that way, and you could explain why that is the number. Volume of ideal gas at 273 Kelvin equals 22.4 liters. So we can use this and take it a step further. Suppose you want to know what is the value of R? Where does R come from? I mean, you just look it up in a table, right? But somebody had to figure it out. And how did they do that? Well, you can use this. So what I'm going to do now is I'm going to just go from the equation from above, and I'm just going to solve for R instead. So I'm just rearranging. R equals PV bar over, and I'm going to have the temperature in here at 273.15, which is our triple point. And now we're going to sub in PV bar from the graph. R equals 22.414 liter atmosphere per mole. And then we put in the temperature, which is already here, 273.15, just like so. That's in kelvins. Okay, and now we solve. And we get R equals 0.082058 liter atmosphere per mole Kelvin. And that, my friends, is how they get that number that they give you in Gen Chem. Here is a table 16.2 in your supplementary readings, which has R in a variety of different units. That's just FYI. All right. The SI units, which is the next most common one that you might use, is R equals 8.3145 joule per mole Kelvin. All right, so those are the two common ones that you might use. Let's just mark those. There, of course, are others, and that's just a conversion, which I will leave for you to take a look at. All right, so we have now talked about a number of different things about the ideal gases. What about non-ideality? So there is evidence that real gases are not ideal. This should not be a surprise for you. And this is a lot of the story of PChem. We come up with the theoretical concept for something we can solve. And then we take a look at what we actually see, and we assume that the difference between the two is, well, where life happens. So let's try to understand how to deal with the evidence for non-ideality, and then what we might do about that. Okay. Non-ideality of gases. So there are a number of things that we could do here. Let me sketch a little machine for you over here. I'm gonna have a cylinder. Oops, that's not a very good one. A cylinder over here. When we get to thermodynamics, we'll see lots of cylinders. All right, we have a cylinder over here. And there are some things we can measure, and there are other things we cannot measure. It's also one of the big things about PChem. Now, I'm sure you're all familiar with measuring the thermometer, so let's just make a little hole here and we'll put a thermometer in here. Okay, so thermometer, there's a little hook on the top, it's a little bolt on there. Right, this is a thermometer. so we can get the temperature. And we'll set this to 273 Kelvin. All right. Now we also going to have a fixed volume. So this is a cover on it, and I'm gonna put this little symbol over here. This is a clamp to keep the cover on. Okay. It's a fixed volume, like those cookie jar clamps. All right. What else could we measure? Well, we also can have a pressure gauge. Do you agree with that? So we have another hole in the cover. And of course, the reason why there are these little circles is because this is the hole in the cover. Okay, so we have some pressure gauge up here. This is exactly what they look like in real life, guys. Right? Exactly like that. This is a pressure gauge. All right, and that's what we have. So let's start with our favorite equation and check again and see what else we can learn. Bet you never knew you could do all this. Okay, given PV bar equals RT. Okay, now let's move everything to one side of the equation. Move all variables to one side. So if I divide out by PV, what's PV divided by PV? Well, it's 1. So I'm going to have 1 equals RT over PV bar, like so. Now it says it's the other way here. PV equals RT. Sorry, I'm going to switch it. I'm going to do it the other way. Do you agree that I could also divide PV over RT the other way, right? I could move it on either side and then flip it. So I'm going to do that. PV over RT. By measuring the deviation from 1 for a real gas, then I could check the non-ideality. So did you see that how I got this equation as I just moved everything to the same side of the equation. Now what I want to do is I want to plot everything and ask the question whether or not I have something that's not the same as this. That's the strategy. So let's start by measuring the deviation from 1 for PV bar over RT for a real gas. We'll just assume that everything else is non-ideality. The non-ideality is observed. And let us now define something called the compressibility factor. And that's exactly what it is. It's this moving everything over to one side. And it is going to measure the ideality. Called the compressibility factor. Again, triple equal sign. Because it's a definition. This is the factor to measure this non-ideality. It's really just a measure of what that looks like. Okay, so now let's make a graph. So what you do is you plot the actual and you plot the ideal one. Okay, so for an ideal gas, the compressibility factor, that is the non-ideality, shouldn't exist. So that means that it should be 1 to 1. This is ideal gas. You get the equation y equals x, which is right on the diagonal. That goes right through 0. Okay, but what you get in a real gas is something more like this. Okay, this is some experimental gas. That's the one you're testing. Okay, so what happens down at the bottom? This is attractive forces. will dominate at low temperature. Because why? Because the particles are close together. Up at the top, the repulsive forces will dominate. And so it goes in the other direction. The real gases do not behave ideally, because if they did behave ideally, the actual pressure that you would measure would match the actual Z, right? So you see that we can use this device here, right, where we can measure the pressure of the gas, and you can set the temperature constant. That's how you get this graph. Now, what you do is realize that the real gases don't behave ideally, because there's going to be the interactions. There are two regimes for the real gases, the attractive and the repulsive, which is going to give rise to the shape that's shown. And when we do things like make force fields to do molecular simulations, which my lab cares about, this is one of the ways that we get information about it. So there are ways that we can correct for this. And the first one is called the van der Waals equation. This is a pretty simple one. I have even heard it before. So you can correct for non-ideality. First one is the van der Waals. So let's take a look at what the van der Waals equation looks like. It looks like this. P plus A over V bar squared. V bar minus B equals RT. P equals RT. Looks familiar, doesn't it? So essentially what you have is you have some correction factors. Let's just take a look at what's going on here. We have these correction factors. It would be determined experimentally. In other words, they just made up a fudge factor and they measured it by doing that experiment I just showed you. And that's where the information comes from. A and B are van der Waals constants. Particular to each kind of gas. So how do you get them? Well, you measure each gas separately. And they more or less just correct for all the assumptions. A corrects for the interaction of particles. And B is going to also correct. So let me just tell you a little bit about A. So A is actually defined with an equation, 2 pi Avogadro's number squared C sub 6 over 3 sigma squared. 3 sigma cubed. All right, so there's a few things in here you may not know what they mean. So let's just define our variables. So you already know what 2 and pi are. And sub A is Avogadro's made number of particles in a mole. All right, C6 is something new. This is an interaction term from a model we haven't discussed yet, which is called the Leonard-Jones term. I will tell you more about that soon. Stay tuned to learn more about Leonard-Jones. But basically, it's a model about the interaction of the gases, and the C6 term is going to tell you about the interaction. Now the sigma, this 3 sigma cubed is going to be the radius, is the radius. And that is where that comes from. All right, so this is correcting for one aspect of the non-ideality. We have another aspect, and that is the B. B corrects for the volume. Right, because we had assumed point masses. So now we need to make a correction for that. So B equals 2 pi sigma cubed over 3. Does not look very tidy. Let me try that again. The sigma here. Cubed over 3 times n sub a, Avogadro's number. Yeah, so recall, let's just, if you are thinking about the math here, I will just put what is the volume of a sphere? 4/3 pi r cubed times NA. Just as a little note on the side. This is the spherical volume. So this equation should make sense. All right, so these are sometimes called equations of state because they're talking about the state variables, which are the variables that are, we have more to say about that in thermodynamics. They're the variables that are not going to change depending on how you get them, is essentially what that is. So there is another equation of state, which is like a correction on the ideal gas, and that is called the Redlich-Kwong equation. And it works the same way that the equation for van der Waals works in terms of what you would use it for, right? So you would use it as a correction to the ideal gas equation when you had information about a real gas. There are also others. And one challenge I gave previous students is I let them make their own, which you might want to do. Non-ideality equation. All right, and this one also is going to look a little bit like PV equals nRT, but a little different. So let's see what this one looks like. RT over V bar minus beta minus A. It's an A over temperature to the 1/2 V bar. Man, this is getting complicated. V bar plus beta. How did anybody ever think of this thing? And this has parameters that are lookup, right? And there is also another one called King-Robinson. And again, you would use it the same way. How many of them are there? Well, I mean, basically, anybody could make one. You could make an ideal gas correction law yourself, or a whole rule. This one has an alpha, and then it looks like this. V bar times V bar plus beta. Complicated formulas, right? Why are we looking at all matter? V bar minus beta, like so. Okay. Alpha is dependent, and beta is a table lookup value. So why do we mention all of these things? Okay, and also this is table 16.4 in your supplementary readings, in case you need the numbers. Okay, so this gives you a way to correct for the non-ideality. You could use any of them. The nice thing about the van der Waals is there is actually a physical interpretation for what the corrections mean, right? So if you were to make a model of how the gases interact and you wanted to do this, you want with one that is more fundamentally physically based, because there are reasons why these things are here. The Rietveld-Kwong and the Ping-Robinson both have empirical observations, right? So you measure it for a gas and say, well, I wonder what that number would be. Let's plug it in and make the equations do what we want them to do. And that's how they work. So let me give you an example of how you might actually go about using this. Example. So use the Rietveld-Kwong equation to calculate the molar volume of ethane at 300 Kelvin and 200 atmospheres. This is what we would do. So we would take our equation, and then it basically just becomes a plug-in, right? So we would take and we substitute in the values. So we get V cubed minus RT over P, V bar squared minus beta squared plus beta T, P minus A over T to the 1/2 power square root of T times P times V bar minus AB over T to the 1/2 P equals 0. All right, a lot of these basically turns into a plug-in problem, which I will leave some of the details for you to do. So we need to go to the table and we look up the values for ethane. And we find, so these would either be given or have to supply the table 97.539 and B equals 0.045153 decimeters cubed per mole. All right, and then we do some algebra here. So I think I will, in the interest of time, leave that for you to plug in the numbers. But when we work all of this out, we should get, we'll get something like this. So let's plug in an algebra happened. You'll get V bar cubed minus 1231 V bar squared plus 0.02056 V bar minus 0.00, that's a 1271 equals 0. Huh. This is a cubic. Did you solve these in algebra class? How do you solve these? Well, there are methods for solving the cubics, and it generally involves trying to do factoring and all these things, which is a bit complicated. I mean, I'm sure you could learn this, but we have graphing calculators these days. So you can solve it algebraically if you wish, or it can be solved like that. It can be solved by finding the zeros of a cubic. An easy way is graph and look at your calculator. And that's how you can solve this. All right, this is actually a pretty good stopping point for today. So let us just step back and see what we have talked about today. So we have taken heat equals nRT, something that you probably heard about in high school or maybe even middle school. And it's very familiar. It's great because you just sub in numbers. Like it's great for plug and chug kind of stuff. They love it for intro physics classes because it means something and is historically relevant. But there's a lot more to it than we have than you have seen there. And also, we're going to be continuing to see the ideal gas equation propping up in a variety of different places as we talk about a number of other kinds of situations. So when we get to thermodynamics, when we get to trying to understand how we might want to model various things, we're going to oftentimes turn to the ideal gas now that we're moving into the macroscopic world because we have finished the quantum mechanics. So we saw about making the molar version of PV equals nRT by using that V bar, which sneakily switched it into working in the intrinsic properties instead of being extensive, because now it will all just depend on, well, it won't be dependent upon how much material you have, which is very interesting. We saw how we could calculate the pressure and understood a little bit better how the mercury thermometers work. We did some derivations here that told us some cool stuff that probably things that people have just given to you before. So we understood how we can do the linearization of equations, which is useful for answering some of these questions. We saw that we can take a look at where absolute zero comes from, which is what this graph right here is addressing. And we do that by the y equals mx plus b linearization, and we take the limit. We also saw how we could derive the volume of an ideal gas. So we've told you it's 22.414, but how do you know that? Well, here we can show you how you can actually get that. And we do that relative to the triple point. The other thing we took a look at is how do we get R, right? The ideal gas constant, which we have just simply written out, or it's a lookup value. But now you can understand where that actually comes from, and it can be derived from the principles of the ideal gas law to understand what that is. We also talked about how we can measure the non-ideality of gases. So if you had a chamber that is a fixed volume and you set the temperature, then you measure the pressure of various gases, right? You fill different gases into this chamber and you take some experimental measures. And what we saw is that we can take advantage of rearranging an equation. So you put all the variables on one side and it should be equal to 1. And you go ahead and do the plotting for what you actually got out. And what you see is that your curve is not going to necessarily look like a straight line. It is much more likely to look like a curve. And as you vary your pressure, you will see what happens under non-ideal and increasingly ideal behaviors, right? So in low pressure, the attractive forces are going to dominate, and then we're going to have the repulsive forces dominating under these conditions. So then, seeing the gases are non-ideal, we might want to do something to attempt to correct for this. So the van der Waals is one correction that can happen. That attempts to do this using actual first principles, things that you can look up, physics, right? So we attempted to do that with some physics, and that is our one way we could attempt to do this. So the A and B correction factors actually have physical meanings. The Ping-Robinson and the Riedel-Kwong are other attempts at doing this, but their values are not necessarily actually based on physics. They are based on measurements, right? Empirical observations. So those are two different approaches into understanding how things are working here. And they are two different approaches to doing things like making force fields, to do molecular simulations. And we will see that these will show up as we try to explain some of the things we will see in the thermodynamics. So then I gave you the outline of an example of using the Riedel-Kwong equation, which essentially boils down to plugging in a bunch of lookup numbers. All right, my friends. Well, thank you for joining me while I'm at the conference and for your patience with all of these things. Also, I hope that you have gotten your test scores, because I did grade those up before I left. Did you see that I gave you your scores? Hopefully. They were, for the most part, they were excellent. There were many that were very good. So I know you don't have your test back yet, but you should have those scores available to you, and I'll certainly be giving you a test back as soon as I'm back on campus, so you can see, exactly how that all works out. But I was very pleased to see all of your progress, and I was very happy about that. I'm going to get back to conferencing, and I will be heading back your way, and I should be back. I should be getting back in a week from today, be about Monday afternoon or evening or so. I hear there's another storm on its way. So hopefully everything will go as planned. For Thursday, you have wonderful water. Okay, this is a pre-recorded video that is linked on the Moodle page. I will also upload this recording that I just made now, because I know that this is not our normal meeting time. Understand that others may not have been able to be here, and perhaps you want to refer back to it. So we will do that, and I will be sharing that with you. And of course, we will have plenty of time to discuss any of these things if you wish to go through it again as soon as I am back on campus. All right, well then, thanks so much for being with us, and hope you have a great rest of your day. Hope you're surviving the snowstorm. If you do have a few questions, I can stick around for a couple of minutes. Otherwise, I'm going to get off to this meeting. Oh, you're so welcome. Thank you, guys. Thank you. Good night.